Marhaba. In this video, we want to talk about different kinds of propositions or compound propositions. Okay, so in this talk, or usually when we say propositions, we mean compound propositions. Remember, what do we mean by a compound proposition? It's a statement that we build in propositional logic, starting with the propositional variables and connecting them using the logical connectives or logical operators. Okay, so for example, P, the propositional variable P, is a proposition or a compound proposition. Now, and Q as well. Okay, now we can connect them with the conjunction operator, so we can get P and Q, or we can connect them with P or Q with the disjunctive connective. Now look, this is a proposition and this is a proposition. We can connect both together with, say, the implication operator. So now we have a new statement which says if P and Q, then P or Q. Now this whole thing is a compound proposition, so I can take it as one proposition and say I can take its negation. And then this is a new proposition. I can say I can continue building this proposition by saying, for example, this implies, or if and only if, the proposition are. Okay, so now look at, we got this complicated compound proposition, and this is a statement in a propositional logic. In the same way we build sentences in our natural languages, like in Arabic and English or any other language. Okay, so this is a compound proposition, and we want now to categorize, classify these compound propositions into three types. So let me give you the definition of these three types. So the definition: one, we say that a compound proposition is called a tautology. A compound proposition is a tautology. Okay, so this is the new concept in this video. If the compound proposition, if it is always true, it is always true, so no matter what truth values we assign to its constituent propositional variables. Okay. What truth values we assign to its variables, propositional variables. We assign to its variables. Okay. So you see here, for example, this is a compound proposition. Now you have to try that. So what are the propositional variables here? We have P, we have Q, and we have R. Okay, so we have three propositional variables. No matter this whole big statement, a compound proposition, we will call it a tautology if no matter what you assign for P, Q, and R, so you can assign P to be true, Q to be false, and R to be true. In every single assignment you try to assign values for these propositional variables, you must get a true value. That's what we mean by it's always true. Okay. So well, it could be always true and could be not. You can find an assignment which makes it false. But if every single assignment makes it true, then we call it a tautology. Okay, we will see an example. Now, the second type of a proposition, it's called a contradiction or a fallacy. So a proposition, so again, when I say proposition, I mean compound proposition. So a proposition is called a contradiction or fallacy if it is always false. Again, in any assignment of truth values to the propositional variables, to the building blocks of the compound proposition, you always get a false value. If this happens, we call the proposition a contradiction. Now, a proposition which is not a tautology and not a contradiction is called a contingency. So contingency. It's a proposition which is not a tautology nor a contradiction. Okay, so this is a contingency. Now let's think of these three concepts or using truth tables. So we have a tautology, we have a contradiction, and we have a contingency. Okay, if you look at the truth table of a proposition, how do you know if it's a tautology? Well, you look at the column in its truth table, and if every single entry is true, then it's a tautology because it's always true. If every single entry is false, then it's a contradiction. Now, when do you know it's a contingency? If it's not a tautology, so not every entry is true and not every entry is false. So this means you have to have at least one true and one false in the column under the proposition in its truth table. Okay, so this is a contingency. Let's have an example. Okay, let's look at this example. What do you think of the proposition P or not P? Okay, so this is a proposition. It's made of one propositional variable. So how do we build it? First we get P, we get its negation, and then we take the disjunction with P. Let's see, is this proposition always true to see if it's a tautology? Okay, let's look at truth table. So P could be true or false. Now, what do we know about not P? Since P is true in this scenario, then not P should be false, and in this case it should be true because P is false. Now let's find out the value of P or not P. Let's see, P or not P. So this column, disjunction, this column, true or false is true. This is because this is how we defined disjunction. Look at the definition of disjunction. We said a disjunction is true if at least one of them is true. So here, this one is true. In the second row, not P is true. So the whole thing is also true. See, now we look at the column below the proposition and we see it's always true. In this case, there are only two scenarios for P or not P, when P is true and when P is false. So it's always true, and so this proposition is a tautology. So P or not P is a famous example of a tautology, which means it's a statement which is always true. So for example, suppose P says it's hot outside, then what is P or not P? It says either it's hot outside or it's not, and this statement is always true. Okay, now let's look at another proposition. Let's look at P and not P. Now remember, how did we define the conjunction? We defined the conjunction to be true only in one case, when the two parts are true. Now true and false is false, because the second one is false, and false and true is also false, because the first one is false. And you see here that this proposition is always false. There are two cases when P is true and when P is false, and the whole thing is always false. So this means that this is a contradiction. Okay. Now, what do you think? Let's have another example. What do you think of this proposition? P implies Q. Okay, we know the truth table of P implies Q. Remember, we have P, Q, and P implies Q. Here we have true, true, false, false. Here we have true, false, true, false. These are all the possible scenarios in which we can assign truth values to the constituent variables P and Q. We know that P implies Q is defined to be false only in one case, when the hypothesis P is true and when the conclusion is false. So in this situation, so it's false here, otherwise it is true. So you see, now look at the truth table here in the column of this proposition of P implies Q. It's not a tautology because it's not always true. See here, it's false in this situation. And it's not a contradiction because it's not always false. It's true here, for example. So this means that P implies Q, this proposition is what? Is a contingency. Because it is not a tautology and not a contradiction. Okay, let's have another example. Okay, example. Determine whether the following proposition is a tautology or a contradiction or a contingency. Okay, look at this proposition which is built from two variables, and it says P implies P or R. So is this a tautology? Is it a contradiction? Is it a contingency? Okay, to check if it's a tautology, we need to check that it is always true. And always means here we have four scenarios, because we have two values for P, true or false, and we have two values for R. So let's see. Let's build its truth table. So here is P, here is R. P could be true, true, false, false, and here R could be true, false, true, false. So we have four scenarios. When P is true, R is true. When P is true, R is false, and so on. Now let's look what is P or R. P or R is true when at least one of them is true. So only false in the last scenario, last case. Now this is our desired proposition. It's P implies P or R. So it is what? It is this column, P implying P or R. Now true implies true is true, right? True implies true is also true. False implies true is true. Remember, we defined an implication to be true if its hypothesis is false. And here false implies false is also true because the hypothesis is false. So what do you notice here? That our proposition P implies P or R is always true. This means that this is a tautology. So this statement, no matter what you do to it, no matter what truth values you assign to the variables, you will always get the output true. Okay, if you want to think about machines, if this, let's call this alpha, this sentence. So if this is alpha, it has two inputs, right? One for P and the other for R. No matter what you put for P, true or false, or for R, the output is always true. No matter how you play with the inputs, this machine alpha will always produce a true value. Okay. Now, okay, so notice that okay, let me now erase alpha and look at our proposition P implies P or R. This is an implication. What is its hypothesis? It is P. And what's is its conclusion? It is P or R. Let me call the hypothesis alpha and the conclusion beta. Okay. So we have a compound proposition of the form alpha implies beta. And we saw that in this case, alpha implies beta is a tautology. It's always true. I want to discuss with you now another way to decide when an implication is a tautology without constructing its truth table. Okay, we want to show that these two statements say the same thing. Okay, one, alpha implies beta is a tautology. So now here, what are alpha and beta? Alpha and beta are compound propositions. So alpha, beta are compound propositions. We just say propositions. Okay, so here, look, in this example, alpha was only P and beta was P or R. Okay, now we have a proposition alpha, we have a proposition beta, we can construct a new proposition alpha implies beta, and we want to see when this alpha implies beta is a tautology. It's a tautology if whenever the hypothesis alpha is true, whenever alpha is true, its conclusion is also true. Beta is also true. So I'm saying that these two statements, 1 and 2, say the same thing. Either both are true or both are false. Okay, so this will give us another way to determine when an implication is a tautology. To show that an implication is a tautology, all what you need to do is show number 2. So assume the hypothesis is true and then show that beta, the conclusion, must be true. Okay, let me explain why this is the case. So how do we show that two statements have the same value or say the same thing? We assume the first is true. So suppose one is true, we show the second is true, and vice versa. We assume the second is true and show that the first is true. This shows that either both are true or both are false. So let's assume one is true. So assume alpha implies beta is a tautology. This means that alpha implies beta is always true no matter what values we assign to its constituent propositional variables. Let's show that statement 2 is true. Whenever alpha is true, beta is true. So suppose alpha is, now we want to show this, whenever alpha is true. So suppose alpha is true, suppose alpha is true. So what do we have here? We have alpha implies beta, and it's a total, and alpha is true. So alpha has a true value, and we know no matter what, now what truth value can we assign to beta? Either true or false, right? But suppose beta is false, then true implies false is false. This is the only situation where implication has a false value, right? When you have a true hypothesis and a false conclusion. But we have a problem here because we assume that alpha implies beta is a tautology, which means this is always true. So beta can't be false, right? Because if it were false, then the implication will be false, and we know that alpha implies beta is a tautology. It's always true. So this means that beta must be true. And this shows that when alpha is true, beta must be true. This is assuming that alpha implies beta is always a tautology. It's always true. Okay, so this is step 1. Now step 2, we want to show that suppose whenever alpha is true, beta is also true. We need to show that, so whenever alpha is true, beta is true. And now, based on this assumption, we need to show that alpha implies beta is always true. Okay, look how we will proceed. Alpha is a proposition, so it's either true or false. If alpha is false, then the whole thing is true, because when we have an implication with the false hypothesis, the whole implication is true. So we're done with the first case. The second case is when alpha is true. Suppose alpha is true. But we assume that whenever alpha is true, beta is true as well. So beta is true, and this means that true implies true is also true. So we showed that in all possible scenarios of alpha and beta, the whole thing, alpha implies beta, must be true. So it's a tautology. So therefore, alpha implies beta is always true. It's a tautology. Okay, maybe this is a bit confusing, but moral of the story, to show that alpha implies beta is a tautology, all what you need to check is that whenever the hypothesis is true, the conclusion must be true. So let's check this on this example. So remember, let me do it in a new place. Okay. So we want to show that P implies P or R is a tautology. Okay, we constructed the truth table and we found out that it's always true. Now another way to show that it's a tautology is to check whenever the hypothesis is true, its conclusion must be true. So suppose the hypothesis is true. So suppose P has a true value. Now we need to show the conclusion. What is the conclusion here? P or R. So now the conclusion will be P or R, but since P is true, this will be true or R. And notice that true or R, what is R? R could be true or false. So it's either true or true, which is true, or true or false, which is also true. So regardless of the value of R, whether it's true or false, the whole thing will be true. So we showed that if the hypothesis P is true, then the conclusion P or R is also true. This shows that P implies P or R is a tautology. Okay. So moral of the story, to show that a proposition of the form alpha implies beta, so an implication, is a tautology, you either construct the truth table and show it's always true, or you write an argument showing that if you assume alpha is true, it follows that the conclusion beta must be true. And in this situation, alpha implies beta must be a tautology. It's always true. Okay. This is the end of this video.